Hi, everyone. In a previous video that I just put together, I went through a demonstration of binary logistic regression where we included two predictors of a binary outcome variable. And in this video, what I wanted to do is to provide a little bit more complex demonstration of how to perform binary logistic regression using SPSS. And in this case, instead of just having two predictors, we're going to have multiple predictors, one of which is a multi-categorical predictor variable. So before I get started, I do want to mention that underneath the video description, you'll find a link to the SPSS data file that I'm working from. So you can download a copy of that data to follow along. There will also be a link to a PowerPoint that's going to go into a lot more detail than I'm going to be covering in this video. My last video, I went into a fair amount of detail on things, but still reserved much of the more complex issues for the PowerPoint. And I'm going to do the same thing here, but we're actually just going to kind of keep this more generally a more simpler presentation. So I'm going to focus a lot more on just the mechanics of how to run the analysis and some of the general interpretations, but I do leave a lot of the more substantive interpretations to the PowerPoint. So I do encourage you to download a copy of the PowerPoint. I'll also include a link underneath the video description to my previous video in case you want to start there and then proceed with this one. So the data that we're working from is from a study from 1987 on labor force participation for women. The data was from the 1976 panel study of income dynamics. So it comprises 753 white married women aged 30 to 60. And in terms of the variables, our binary dependent variable or outcome variable is this LFP variable that you see right here. So it's LFP, and that's indicating whether a woman is in the paid labor force. And this is as of 1976. So this is a long time ago. So just kind of keep in mind, differences in how we kind of approach some of these things nowadays as opposed to then. So anyway, this particular variable is coded 0 for no and 1 for yes. We have this K5 variable right here, which is the number of children under 6 years old. So we also have this K618 variable, which is the number of children aged 6 to 18 years old. We have the age cat variable right here. So this is our categorical variable. And we have 1 represents a woman who is between 30 and 39. A 2 represents a woman who's between 40 and 49, and 3 aged 50 plus. We have this WC variable right here, which is a binary independent variable indicating whether a woman had attended college. This is coded 0 for no and 1 for yes. We also have HC, which is a binary independent variable indicating whether the husband had attended college. It's coded 0 for no and 1 for yes. Then we have this LWG variable right here. This is a natural log of what the woman's wage would be if she was employed, given her other characteristics. And the last variable is this INC variable. This is family income of what it would be if the woman was not employed. So just kind of a visualization of the model you can see below. And the age cat variable, when we run our analysis, what we're going to have happen is that the program is going to internally recode the age cat variable into 2 dummy variables, which you'll see right here and here. So the composite variable, or kind of the overall variable, is reflected by those 2 dummy variables. This example too was published in Long and Friese's book on regression models for categorical dependent variables using Stata. So I was just able to import the data into SPSS and thought I would provide their demonstration here. So let's go ahead and open up SPSS and run our model. Okay, so here's our data set, and so this is our outcome variable right here, whether a woman was in the labor force or not. Again, 0 indicates a woman not being in the labor force, 1 indicating that she was. This is our K5 variable, K618. We're not using the age, but rather we're using this age cat variable over here. So there's the previous college or having college, husband having college, there's the log wage, and there's the family income. So let's go ahead and click on Analyze. We'll go down to Regression, Binary Logistic right here. We'll move, you can already see the labels are actually associated with each of the variables, so maybe it makes it a little easier to follow along. In paid labor force, so we're going to move that to the dependent variable box, so that's our LFP variable. Number of kids less than 6, that's our K5 variable. Number of kids between 6 and 18, that's our K618 variable. Wife attended college, we'll move that over. Then our husband attended college variable, log of wife's estimated income right there, and then family income excluding the wife's, which is that one right there. We're going to move the age cat variable over. Now, because the age cat variable is being treated as categorical, we're going to need to go up to the categorical box. We'll click it, and we'll move that variable over to the categorical covariates box. So the default, where it says contrast, it's set for indicator. And basically what's going to happen is that we're going to be generating dummy variables to represent the age cat variable or our age variable. The first reference category, or the default for reference category, is the first level on that particular variable, which is going to be those women that are aged 30 to 39. If we click last, then the reference category would be the 50 plus group, but we're going to stick with the first right here. So we'll click on continue. Under options, we'll go ahead and select Hosmer-Lima show goodness of fit and the confidence interval for the odds ratio. We'll click continue and then on OK to generate our output. So in my previous video, I kind of talked about some of this early stuff in the output. The first part of the output is just basically some general model information. You'll notice down here, it's got the categorical variable codings. And so you'll see that we've got essentially the first dummy variable represented and the second one represented. So in terms of the reference category, the 30 to 39 group, you'll see that these women were coded 0 on both of our dummy variables. For the 40 to 49 group, these women were coded 1 on the first dummy variable, 0 on the second one. And then the 50 plus group, the women were coded 0 on the first one and then 1 on the second one. So we'll scroll down a little bit with the block 0. This is basically information related to a null or intercept only model, and basically this model is used as for comparison against our full model that contains our full set of predictors. So you'll see right down here, it's got this is basically the regression slope for the intercept only model. And so there are no predictors that are actually included in this. So we're just going to keep this in mind as we move forward when I start referring to our full model versus a null or intercept only model. We'll scroll on down and we'll look at the block 1, and basically this is the only block of variables that are included, and you'll see that we have our likelihood ratio chi-square test that's given. So this is our likelihood ratio chi-square test. So the likelihood ratio chi-square is 124.299. The degrees of freedom for our model is 8, and you can see there's our p-value that's given right there. And basically what the likelihood ratio test is doing is it's testing our full model, the fit of our full model relative to the null or intercept only model. So if this test down here, if this is statistically significant, then that would indicate that our model containing the full set of predictors is a significant improvement in fit relative to the null or intercept only model. And that happens to be the case right there. As you can see, our p-value is less than 0.001. With the model summary table, I discussed this in my previous video, but just to reiterate, the -2 log likelihood is the model deviance for the model. It's bounded at 0, reflecting a saturated model where there's perfect fit, and then positive values as we move away from a 0 in the positive direction. That's signifying worsening of fit of our model relative to that saturated model. the model deviance really is rarely ever reported, and it's not really usually a central index of interest, but it is utilized in the computation of other measures. So I'm just kind of rehashing that from my previous video. Here we have the Cox and Snell and Nagelkerke pseudo R-square values. As I said in my previous video, these are analogies to the R-square value that we would have in the context of least squares regression. Basically, they're not computed the same way, so that's why we kind of think about them as rough analogies. And my preference, though, when it comes to pseudo R-square is actually the McFadden pseudo R-square, which unfortunately is not generated through this particular approach in SPSS, but we can kind of trick SPSS into giving us what we want if we go through the multinomial regression route, and I'll show you that in a bit. We have the Hosmer-Limashow test right here, which basically involves comparisons between observed and expected frequency counts within our two levels of our dependent variables. So not being in the labor force and being in the labor force. And so the basic idea is that if our model is doing a good job, then the expected and observed frequency counts should coincide. In which case, the Hosmer-Limashow test, we would not expect that to be statistically significant. If we find it statistically significant, then that's actually indicating poor fit to the data. So you can see right here the p-value for this test is 0.056, which is getting pretty close in terms of indicating poor fit. So we'll scroll down a little bit further, and you'll see we have our classification table that's given. So basically, this is useful for evaluating how well our model does in terms of predicting group membership. So in terms of the output, you'll see we have the observed outcomes. So you could think about the outcomes as coded as 0 and 1, where 1 is the target outcome of interest, which in this case would be being in the labor force. So I'll just call this y equals 1. And the target outcome, or the non-event, is y equals 0, which is a woman not being in the labor force. So the rows represent the observed frequencies and so forth for those two outcomes. The columns are predicted outcomes based on our model. So we have predicted outcome. I'll just designate y hat, set this equal to 0 for the prediction that a woman is not in the labor force, and then y hat equals 1 for the prediction that a woman is in the labor force. So you'll notice that this cell right here and this cell right here, the values in those are basically reflecting correct prediction. So of the women who are in the labor force, 331 were correctly predicted by the model to be in the labor force, and that the accuracy rate then for this prediction is 77.3%. This is referred to as the sensitivity for the model. Of the women who are not in the labor force, 178 were predicted by the model to not be in the labor force. So the accuracy rate there was 54.8, and that is referred to as the sensitivity for the model. So if we sum up if we take the sum of 178 and 331, those two accurate predictions, and divide that by the total number of cases in our data set, that gets us the total accuracy of the model. So the total classification accuracy of the model was 67.6%. So we'll now look at the regression output. So we have the variables in the equation down below. And as you're looking at this, you'll see we have the regression coefficients, standard errors. This is the Wald chi-square tests values that you see right there, degrees of freedom for those Wald chi-squares, and then the p-values. So this is where we can kind of test the predictors in terms of their contributions to the model. Now, I do want to mention that the what we're doing is we are predicting the probability of a woman being in the labor force. That's the target outcome in our model. So, but we can't model predicted probabilities as a linear function of our predictors. So instead, what we do is we're essentially modeling the relationship between our predictors and a linear transform, a transform of the predicted probability, so that we're linearizing that relationship. So what we're effectively doing then when we're interpreting the regression slopes, that we're literally talking about the predicted increase or decrease in logits, which is the transformation I was talking about, as a function of changes on our predictor variables. So the predicted outcome, if you will, is our logits, which are log odds that our case is in group 1. So that's the way to kind of think about it. Since we don't really spend a lot of time making sense out of log odds or logits, you could think about the regression coefficients by looking at the signs, and that gives you an idea about whether lower scores associated with a predictor or higher scores are associated with a predictor are associated with greater probability or lesser probability of being in the target outcome category. So with a negative slope, like for instance right here with the kids less than 6, basically that negative slope that you see right here is conveying that the more kids that a woman had that's under 6, the lower the probability that she was in the workforce. And you can see that that predictor was statistically significant. If we look at and the same slope, the direction is still the same with respect to kids between 6 and 18. There's a negative coefficient there, but you can see that that predictor was not statistically significant. With the wife attended college, you can see it's a positive slope, and we see that it is statistically significant. So keeping in mind the coding of that variable of 0 for not attended college and 1 for attended college, then basically that's indicating that a woman who attended college was more likely to be in the labor force. So if we have a positive slope for husband attended college, but you can see that that was not significant as well. The log of wife's estimated wages, it's positive right here, and you can see it's statistically significant. So basically, higher values associated with this particular predictor are associated with a greater probability of being in the labor force. The family income, excluding the wives, you can see it's a negative slope. So and you can also see it's statistically significant. So basically, families, if a family was going to earn more, excluding the wife's income, then the probability of the wife being in the labor force would actually be lower. Then you have the wife's age group. The reference category was 30 to 39. So we have a comparison between the 40 to 49 group and the 30 to 39 group. And you can see that slope is negative, and you can see it's statistically significant. So basically, women falling into the category of 40 to 49 were less likely to be in the labor force than women in the 30 to 39 category. And then the same basic idea is at play here with respect to the comparison between the 50 plus women and those between 30 and 39. You can see that is statistically significant. The values in the EXPB column right here are odds ratios, which reflect the multiplicative change in odds of a woman being in the labor force per unit increase on the predictor variables. The only difference in that interpretation really kind of comes down here when we're talking about the constant or the intercept. The intercept, if we exponentiate the intercept, we get this value right here, the 2.567, which is the predicted odds for a woman being in the labor force, assuming values of 0 on all of the predictor variables. But the remaining values are odds ratios, which are reflecting changes in odds. And to keep things as simple as possible, just think about it this way, that an odds of 1 basically indicates no relationship between a given predictor, or no systematic predictive relationship between a given predictor and the odds and ultimately the probability of being in group 1. A value greater than 1 signals that a predictor is positively related to the odds, and by extension, the probability of being in group 1. A value between 0 and 1 would reflect decreasing odds associated with changes on the predictor, or increases on the predictor. So you can still kind of keep in mind the positive negative associations that we were using previously when we were referencing the B category. And in fact, you could think about it this way, that if the odds ratio is greater than 1, then basically that's going to be consistent with a regression slope that is greater than 0. If the odds ratio is less than 1, then that would be associated with a regression slope that is less than 0. And then obviously if the odds ratio is equal to 1, then the that would be consistent with a regression slope that is closer to 0. So you can because basically the odds ratio is an exponentiation of the regression slopes. I will mention too that we also have confidence intervals for the odds ratios, where the null hypothesis for the odds ratio is that it is equal to 1. The alternative obviously being that the odds ratio is not equal to 1. So if 1 falls between the lower and the upper bound of a given confidence interval for a predictor, then the predictor would not be statistically significant. Whereas if 1 falls outside the lower and the upper bound, then that predictor would be considered as statistically significant. Okay, so that's just kind of a really general overview. Like I said, check out the PowerPoint because there's a whole lot more detail than I'm really going into right now. So if I want to get that McFadden's that I was referring to, it's really easy to do. We can go to Analyze, go down to Regression, and then go down to Multinomial Logistics. So we can click on that, and we'll move our dependent variable in paid labor force. We'll move it over to the dependent box. Now, in this case, we have to set a reference category. By default, when we ran our analysis through our previous approach, the default reference category was the group that was had the lowest value on the dependent variables, which was our women who were not in the labor force. But in this case, we have to make an active selection. So I'm going to click on reference category here and select first category to keep it consistent. So next we'll click continue, and we'll move our variables over. So we have kids less than 6, kids between 6 and 18, wife attended college, husband attended college, log of wife's estimated income, family income. We'll move those over to the covariance box, and the wife's age group, we'll move it to the factor box. Now, by default, this particular variable is the reference category on this through the internal coding will be the last category. So it would actually be the 50 plus category instead of the 30 to 39 category. And there's no way to really make that change. The overall fit of the model is going to be exactly the same. Where things would differ a little bit is in terms of the intercept, and then also the regression slopes for the dummy coded variables that would be generated. You can, an option around this particular approach is to, actively kind of recode wife's age group into a new variable where the 3 now is a 1, the 2 is 2, and then the previous 1 is now a 3. You could do that. Or you can just kind of create your own dummy variables and include those in the covariance box instead of including the age cat variable up here. Those are some options that you have available if you wanted to go that route. So we'll click on statistics here and select, go ahead and select information criteria. There's classification table, goodness of fit, and we'll click continue and then on OK to generate our output. So as we're looking at this, you'll notice first off, up here we have our likelihood ratio chi-square test. This is a test of the difference in fit between our intercept only and final models. So up here you've got, these are those model deviances I was telling you about, the model deviance for the intercept only model, the deviance for the final model. So the chi-square value that we have right here just is computed by taking the deviance for our intercept only model and subtracting the deviance for our full model. So there it is right there. And again, that model was statistically significant. You'll see we have the goodness of fit test right here. We have a Pearson chi-square goodness of fit test, a deviance chi-square goodness of fit test. And the basic idea behind these when you're testing them is non-significance is an indicator of good fit. So you'll see for the Pearson chi-square test, we have non-significant. So that's an indicator of good fit. The deviance chi-square test is actually significant. So you have a little bit of information maybe suggesting that the model is not a good fit. Just keep in mind when you're looking at all these different indicators of overall fit of your model to the data, they won't always necessarily agree. So this would be a case right here where there's a little bit of a disagreement. But nevertheless, most, the likelihood ratio chi-square test is significant. Pearson goodness fit test is not significant. So both of those are clearly indicating a good fit of the model to the data. When we look at the pseudo R-square table down here, we have McFadden's pseudo R-square. So McFadden's is basically computed by taking the chi-square difference right here. Basically, it's the difference in those deviances that we had just computed. If we take this chi-square value right here and place it over the model deviance for the intercept-only model, then basically that provides the McFadden pseudo R-square. So once again, the chi-square value that you have right here is just basically taking the deviance for the intercept-only model, subtracting the deviance for the final model. So that's the difference in those model deviances. Place it over the deviance of the intercept-only model, and then you basically get a measure of the proportionate reduction in the in lack of fit as we move to the basically with our full model in relation to the intercept-only model, and that's what McFadden's is capturing. Or you could basically you could also consider it the proportionate improvement in fit as a result of including our predictors relative to the null or intercept only model. So you can kind of think about it in those ways. So then we'll scroll down, you'll see that we have likelihood ratio chi-square test, and then down below we have our parameter estimates table. So the parameter estimates table is very similar to what we had before. Like I said, it's now reflecting the difference in dummy coding. You can see that the redundant parameter down here of 0, that's kind of indicated right here, 0, is associated with group 3 as opposed to group 1. And so basically these are comparisons between group 1 and 3 and then group 2 and 3. So there's a little bit of a difference there. And then the intercept would also be different as a result of the difference in coding down below. The likelihood ratio tests are basically a test of each of the predictors in the model, and oftentimes these will be more powerful than the walled chi-square test that we have down here in this table, but usually folks end up defaulting by reporting on the walled chi-square tests. My guess is it's because a substantial amount of the programs, and including SPSS, the main methods for generating results, print out the walled chi-square or the walled Z test instead of the likelihood ratio test. And so it kind of ends up where you have to do a little bit more to get the likelihood ratio test. But nevertheless, as you can see right here, the number of kids less than 6, you can see that that is a statistically significant predictor. And really quickly, these likelihood ratio tests, the way they work is you start out with the full model containing all the predictors, and then you test a model that contains all of the predictors minus the one that you're testing. And so the difference in fit between those two models is captured in the chi-square difference value, which is provided like right here for this particular predictor. And you can see it's statistically significant. So there's a significant difference in fit. It's actually a significantly worse fit of a model that does not contain the number of kids less than 6 variable than a model that does contain it. So that's how the logic works. So at any rate, you can see right there the number of kids less than 6. That's a significant predictor. The wife attended college predictor is significant. The log of wife's estimated wages predictor is significant. You've got the family income excluding wife's is significant. Now you'll notice that the wife's age group variable right here is statistically significant. And so the likelihood ratio test right here is an omnibus test of the overall effect of age category as a predictor within the model. So it's not broken out into those dummy variables like you have in the table below, but nevertheless, it is an omnibus test of wife's age group um, as a predictor. So that's kind of how to make sense out of that. All right, so that's just a really quick run through of these results, basically how to generate these results and our interpretation and so forth. Again, I do encourage you to check out the PowerPoint that's going to provide a lot more detail. So that's going to wrap up this video presentation, and I appreciate you watching.